Everyone, Assalamualaikum warahmatullahi wabarakatuh. So this is chapter 1 plus with chapter 3. So this is for week 1. So this is the introductions. So let me start with the units of the chapter 1. So basically in chapter 1 we will learn something that related to standard of length, mass and time, which we get from the base quantity. And of course, we want to learn about the dimensional analysis, the uncertainty in measurements, and also the significant figures. And we want also to learn the conversions of units, estimates, and order of magnitudes of calculations. So basically, these are the 5 base quantities which start with the length. Okay, the length, mass, time, temperature, and current. So the length with the symbol L have an SI unit of meter with the symbol M. Mass is with the symbol M, okay, short letter M. The SI unit is a kilogram. Time is T, and the SI unit for time is seconds. And temperature is capital T, with the SI unit is Kelvin, with the symbol K, and of course the current is I with the SI unit of ampere, with the symbols of A. From this base quantity we can actually derive a few derived quantities. So that is how we get the definitions of derived quantities from the 5 base quantities. So we can actually derive velocities, acceleration, maybe force, momentums of, or energy. So basically this is table 1.1, which is the approximate values of some measured length. For example, the distance from Earth to most remote known quasar, maybe the remote known of normal galaxies, how many is 1 light years, orbit radius of Earth about the Sun's, the smallest dust particles. So these are the value that actually is not really accurate, because what we call this one is like approximations of the values only. Okay, so to you can see here the diameter of proton, the diameter of atomic nucleus is very small. Okay, sangat kecil. Jadi macam mana kita nak approximate that value when it comes to the object that really small. Right, so this is also the approximate values for some masses. So you can see here, this is like in mass in the kilogram, the SI unit for the mass. Okay, such as we have a Milky Way galaxy. What is the mass of the Milky Way galaxy? It's just an approximation value. Okay, anggaran berat sahaja, bukan anggaran jisim sahaja, bukan anggaran sebenar ataupun bukan value yang sebenar untuk yang tepat untuk setiap objek yang dinyatakan. Okay, so kita tengok lagi. So this is also the approximate values of some time intervals. Okay, this is for time. We have length, we have mass, and of course we have time, such as a time between the normal heartbeats. It cannot be is so very speaking in terms of everybody who doesn't have equal heartbeats. Okay, of course. So that's why this is also the approximation values only. Okay, so this the table 1.4, some prefixes for powers of 10 used with the metric SI and CG as unit, where we have a power, which means the value, the exact value, the prefix name, okay, and also the abbreviations. Okay, these are the 3 important things when we deal with something equivalent to prefix, because we if you just know the name, ada tahu nama sahaja, tak tahu power berapa, tak tahu abbreviation apa, so it's quite impossible, okay, for us to understand. It's just like the question asked here, a human hair has a thickness of about 70 micrometers. Okay, 70 micrometers. How did I know this one is micro? So this one based on the abbreviations. Okay, they use micro. It's like a U, nampak macam U, tapi sebenarnya micro. What is the value of micro? Is 10 to the power of negative 6. Okay, so we can actually see when we deal with something that related to meters or related to length, we can easily convert it to meters or maybe kilometers. So you can do it in your own. Okay, so for example, I have obtained some things, but during my school days I always did it from top to bottom, meaning that from higher value to the lower value. I start with the tera, giga, mega, kilo, deca, deci, centi, milli, micro, nano, pico. That's only what I did during my school days. Okay, Tok Guru memarahi kami dekat Central Market menyebabkan Nani pingsan. So that's what I did. Okay, it's quite funny, but it works for me to understand the some prefixes for the power of 10 used with the matrix. Remember, this is SI unit and also CGS unit. Okay, so this is dimensional analysis. Remember, when we deal with some things that related to dimensional analysis, we want to learn two things. The first thing is we want to see, or we want to check either the dimension whether the equation is correct or not. Okay, to check the correctness of the equations. Okay, for examples, but to determine the dimensional analysis, we must know that it can be done using only three consonants. Okay, consonant like, okay, let me do it. L, okay, consonant M, and also consonant T. I prefer to do it in the capital letters, such as what we did here. So this distance, okay, distance means length. So that's why the dimension for distance is L. Okay, and how about area? Area is actually get from this one. Okay, width times length. Okay, width times length. So the width is also part of length. So therefore, length times width length. So that's why we get L squared. Okay, right? So as for the volume, we have L3 because we have another diameter, as we have another dimensions of L. So L times L times L, you can get L cubed. And how about velocity? Velocity is based on what we learned just now. We should know that velocity is based on length over time. Okay, length over time. So what is length? Okay, so therefore we get L over T, right? So therefore, if we want to see the acceleration is the velocity over time. Therefore, this one over another time, we get L over T squared. And how about energy? Okay, so you can see in the topics of energy, or you can do on your own. You can try it out. Okay, that what is energy? Okay, right. Okay, so I said to you that the functions of the dimensional analysis is to check whether the equation is correct or not. And then number two, we want to get the SI unit for the any parameter or any terms inside the equations. For example, in this question, okay, show that the expression of V equals to V naught plus 80 is dimensionally correct, where V and V naught represent velocities, A is acceleration, and T is a time interval. You can see here, okay, if you want to check the dimensional analysis, you must be able to understand that on the left side we have V. Okay, on the left side we have V, and on the right side we have a V naught and also AT, where you know that V naught is a velocity and A is acceleration while T is time. Okay, so V equals to v naught plus with a times t. Okay, so if you want to check the dimensional analysis, the left hand side should be equals to every parameter or every place on the right side. So every place means that this one is one place and 80 is also considered as one place. So everybody and everything on the right side should be equals to the terms on the left side. So for example, if the term is L over T for the velocities, so that means how about V naught? V naught is also L over T. And how about A? AT. So AT is A is L over T square times with T. Okay, so if we cancel out T and square, so therefore we can get L, okay, is equivalent to everything that is on the right side. So therefore this equation is dimensionally correct. Okay, these are the equations that we can also check the dimensional, either is consistent or inconsistent. For example, we have x equals to x naught plus vt, and we know that x is the distance or maybe the displacement, so x is considered as length. And how about x naught? Okay, naught here is the initial, meaning that initial displacement. How about v? V is the speed. Okay, and of course t. So we can do the first thing first, which we have x equivalent to x naught plus vt. Okay, so what is x? The dimension for x is L. Okay, how about x naught? X naught is also L. And how about v? V is L over t, and t is t. So therefore we can cancel out t and t. So therefore L is equivalent to L on the right side. L is on the left side is equivalent to L on the right side, meaning that the equation number 1 is dimensionally consistent. Okay. Okay. Can you do it on your own for the second and also the third equations, when I will help you in determining the second one. Okay, so let's try it out. Okay, now we have x equivalent to x naught plus v naught t plus half a t square. Okay, so x is considered as length, so that should be L. And if the equation is correct, then of course everything, every places 1, 2 and also 3 places, all must be equivalent to L in order for the second equation to be dimensionally consistent. So therefore, how about x naught? X naught is also L, so it's okay. And how about vt? Vt is L over t times with t and plus with half a t squared. Remember, if you encounter half, half is not a dimension. Okay, therefore it can be cancelled out, and we straight away, okay, go to a. A is already L over t square times with another one is t square. So therefore we can cancel out t square and t square. This one we can cancel out t, and therefore L equivalent to L on the right side. Therefore the second equation is also correct. And how about the third equations? So let me do it. L over t, okay, equivalent to v. What is v? L over t also, and plus half a t squared. Plus half a t, so we don't have to put half, and straight away to a. A is L over t square times with t square. Okay, so therefore t square can be cancelled out with this t square, and obviously, okay, on the left side is L over T, but on the right side is L over T, yes, okay, but in here is only L. So therefore, this, okay, the terms on the left side is not, okay, the same as the term on the right side, because on the right side they have L over T plus with L, and therefore the third equation is not dimensionally correct. Okay, uncertainty in measurements and the significant figures. Accuracy of measurement is limited. For the significant figures, the number of digits in a quantity that are known with a certainty. So number of significant figures after multiplications or division is the number of significant figures in the least known quantity. So basically, if we are encountered as uncertainty in measurements, okay, this one happens during our problems or during our time when we are taking the measurements, okay. So especially for those yang ambil, contoh dia ada orang ambil 3 tempat perpuluhan, ada orang ambil 2 tempat perpuluhan. So please remember that the most important thing in the significant figures is we must take, okay, it all depends on the decimal point that you use, either using the multiplications or divisions when it comes to the um, uh, when it comes to the operation, yeah, for the mathematics. These are the rules. Okay, these are the rules for the significant figures. All non-zero digits are considered significant. Okay, for example, we have 91 have two significant figures, which is 9 and 1, and for the decimal point 123.45, 1, 2, 3, 4, 5. So have a 5 significant figures. So if I, okay, this is for non-zero digits, so meaning that in number doesn't have 0. How about 0 appearing anywhere between two non-zero digits? So for 101.12, 10112, so it may have 5 significant figures. And for the 13.309, it also have 5 significant figures. Okay, we count everything because 0 is in between the number, the non-zero digits. How about the leading 0? Leading 0 means the 0 at the in front of the numbers. Okay, like this part, 0.00052. Okay, 0.00052 has only two significant figures. Okay, meaning that we doesn't count the 0 at the front of the number. If the number is obviously either non-zero, either the decimal point or not. Okay, we didn't count the 0 that will be in front of the numbers. Okay, so we only count 5 and 2, okay, which have two significant figures, right? So the next one will be the trailing zeros. The trailing zeros maksudnya kosong yang berada di belakang. Okay, in a number containing decimal point are significant. Okay, please remember when you are giving, or you are writing a number of 12.2300, so this that 0, okay, that you put after the 3, after digit 3, is also considered as significant figures. Okay, so in this case we have 1, 2, 2, 3, 1, 0, 0. So 1, 2, 3, 4, 5, and 6. So must have 6 significant figures. But for the trailing zeros, okay, like this one, 0.000, 1, 2, 2, 3, 0, 0. Again, the trailing, the leading 0 here is not counted as significant figures. Why? Because it's, okay, it is all because of this one. Leading zeros are not significant, but okay, after the number, after we count 1, 2, 2, 3, 0, 0, these both zeros, okay, yes, or we have to measure, we have to make sure that we count that the trailing zeros, okay, on the decimal point which also considered as significant figures. So in this case, 122,300 is considered as 6 significant figures, while for 120.00 has 1, 2, 3, 4, 5, 5 significant figures. And the last one, but the significance of the trailing zeros in a number not containing a decimal point can be ambiguous. What does it mean by the ambiguous? Meaning that we will have more than one answers. Okay, for examples, we have 122,300. So basically 122,300 has 6, 1, 2, 3, 4, 5, 6, 6 significant figures. Okay, but how can you make sure that according to this statement, okay, this value, this number, okay, have 6 significant figures and or 4 significant. How to get 4? So when you want to get 4, these trailing zeros for the number that not containing a decimal point, as you can see here, without no point, okay, we can actually uh, change it to the scientific notation form. And scientific notation form, we know that when you have a trailing zeros, so the decimal point should be on the last part. Okay, so you can consider 1, 2, 3, 4, 5. So we can actually write down this value into the scientific notation 1.223 times with 10 power of 5. 1, 2, 2. So now we don't consider this. Okay, we don't consider this one, but we consider this. Okay, according to the decimal point, now we have 1, 2, 2, 3. So therefore we can get 4 significant figures, and it will be a different thing if we write down as 1.22300. So this number will give you how many? 6 significant figures, because remember about the trailing zeros, for the decimal point we must count everything into our consideration. Therefore this one have 6 significant figures. This is very good examples for how can you determine or how to use the significant figures in the real problems. So for example, we have a problem of several carpet installers make measurements for carpet installations in the different room of restaurant, reporting their measurement with the inconsistent accuracy as compiled in the table 1.6. So this table, so in this table we have a dimensions of room, of the banquet hall, a meeting room, and also dining room with a certain length and width. And of course, according to the questions, the installers have made the measurements, and of course there is inconsistency in terms of how they write down the width or the value. Okay, if you can see here, and as I can pick one only, so for the banquet hall the length is 14, okay, 14.71, and the width is 7.46. Okay, now as we learn the significant figures, the length should have how many? Okay, should have 4 significant figures, while for the width, okay, of the banquet hall is only 3. And of course, if you want to get the measurements of the area of the banquet hall, we must times the length and the width. So you should times the length and the width, and of course the final answer for when we times the 14.71 to 7.46 will be 109. So we get 109.74. Okay, so that will when we punch the calculator, okay, kita tekan calculator, we get 109.74 etc meter square. Okay, meter square, don't forget about the unit, right? Okay, 109.74. This one okay, we have 5 significant figures. Am I right? Okay, but in terms when you see the questions, okay, taking into account the significant figures, okay, taking into account the significant figures, so therefore we must make sure it follows the significant figures rule, which means if there are involving, okay, the question involve mathematical operations which are multiplications or divisions, so we should at least we should write down the answers in terms of the least significant figures. Okay, 4 and 3, we compare 4 and 3, now we get 3. 3 is the least one. Okay, so 3 is the least one, therefore we should convert 109.74 to only, instead of 5 significant figures, we should convert it to 3 significant figures. So in this case 109, but 9.7, 0.7 is already past 5, therefore we should get 110. So 110 is considered as 3 significant figures, so meter square. So that will give you the accurate answer in terms of calculating the area of the banquet hall, but taking into account the significant figures. So you can do the rest of the meeting room and also dining room on your own. Okay. Okay, so these are the problems that involve the mathematical operations, which is additions. So remember, the number of the decimal places after additions or subtraction is equal to the smallest number of the decimal places in any of the individual terms. So therefore, if you try to count 16.74, okay, 16.74 plus with 5.1, the answer will be 21, okay, 21.84 seconds. Okay, this should be your answer, and of course this is this is 2 decimal point, and this is only 1 decimal point. So according to the Einstein, little Einstein over here, saying the number of decimal places after addition or subtraction. Okay, this one is addition. Okay, tambah ya, is equal to the smallest number of the decimal places. So which one is smaller, 1 or 2? Definitely 1. So therefore we should put the final answer is according to the according to the rules of the decimal point, then it should follow the least decimal point, which is 21.8, because the decimal point is the one after the decimal point. Decimal places is the one that we count after the decimal point, so therefore we should write the right answer will be 21.8. Okay, how about this one? Okay, can you calculate it? Okay, right, 12.7 plus with 7.25, and the final answer should be 19.95, and these have 2 decimal point, but according to the questions, according to the individual terms, 12.7 have 1 decimal point, while 7.25 have 2 decimal point. So we should get only 1 decimal points allowed in order for us to understand to write the answer. Therefore, we should put 20.0. Okay, the final answer should be 20.0, because 0.0 is also considered as 1 decimal point. Okay. Now we move to the scientific notations. The leading or trailing zeros can make it hard to determine a number of significant figures. Okay, such as 2500 or maybe 0.00036. And remember, 2500 is the trailing zeros, while 0.00036 is the leading zeros. Okay, so it's quite hard to measure the significant figures, so therefore we introduce to you the scientific notations. Okay, the scientific notation write this as a number from 1 to 10 that multiply by a power of 10, making the number of significant figures much clearer. For examples, we have 2500, then you should know that 2500 actually have a invisible decimal point which been put at the end of this zero. And of course, when we want to go to scientific notation, we should write down from 1 to 10 numbers, which means we have to, okay, undo the zero. 1 2 3. Okay, how many? 1 2 3 to get to 2.5 times with how many times that we move the points of the decimal point? 3. So therefore 10 to the power of 3. Okay, if we write the 2.50, then this value, okay, I should clarify to you that 2500 is ambiguous significant figures. Why? Because in this part, okay, we write down as 2.5, therefore we must it is equivalent to 2 significant figures, while if we write down, okay, you just add another 0 to the back of 2.5, so it becomes 2.50, and now it has 3 significant figures. Okay, and how about 0.00036? Now we move the decimal point to the between 3 and 6, so we move to the right. 1 2 3 4 5, so therefore 3.6 times 10 to the power of -5. So 3.6 is the number from 1 to 10 multiplied by a power of 10. So that is how you write down the scientific notation. Okay, the last digit for the round off error. Okay, the last digit in a calculated number may vary depending on how it is calculated due to the rounding off of insignificant digits. Examples, when we have 2.35 times with 5.89 that divide with the 1.57. So if you are going to multiply 2.35 times with 5.89, then you will get 13.842. And after you try to round off it, it becomes 13.8. Okay, 13.8. And of course 13.8, when you divide with 1.57, then the final answer should be 1.7898, and after the round off it becomes 8.79. Okay, that's how you did on the first part, which means you round off the 13.8. Okay, but what happened if we doesn't do the round off at the very first step, but we do it only in the final steps? So how can we get the different answer? So if we try to divide 5.89 with divide with the 1.57, so the value will be 3.7516, and after the round off we get 3.75. You can see here, okay, we actually have get 2 decimal points instead of only 1 in here, 13.8. Okay, so 2.35 times by 3.75, so we get 8.8125. When the round off, it becomes 8.81. Same questions, but you have 2 different answers. That's all due to the round off error. So that's why you must be very careful when you calculate some things in the future, maybe in the next chapter. So make sure that you don't round off early. Okay, you just do the round off until the end of the final answers. Okay, now let's move to the next part of the chapters, which means the conversions of units. So we actually already learned these things during our school days, but unfortunately we still get stuck somewhere else. We try to solve the problem using the conversions of unit, but it's very useful for us to understand the concepts of how to convert the units. Okay, because in physics we may use a lot of conversions, unit conversions afterwards. That's due to our uh, uh, ability to solve the problems. Okay, so if the question asks you to convert the 316 feet to meters, okay, 316 feet to meters, so 1 meter is equivalent to 3.281 feet, and of course we should get these conversions earlier, so that we know how to convert 316 feet. So 316 feet, if we bring down the conversions of 1 meter to feet over a bracket over here like this, okay, if you wish to convert from feet to meters, meaning that the final answer should be meters, not feet. So therefore we should take feet away from the calculation. So how to cancel out feet? So make sure that you should understand that the feet here is on the upper side, or what should we call as numerator. Okay, this one is numerator, and the 3.821 feet is the denominator, what's in behind the per value. Okay, so 316 feet. So if you want to cancel out feet, you should put 3.281 feet at the bottoms of the conversions. You can easily put, okay, uh, otherwise, like this one, 3.281 feet, okay, at the top, and of course put the meter down here. But if you had wish to times with 316 feet, okay, so it cannot cancel out, yeah, left and right. Okay, if you wish to cancel out the feet or the any units at the top of, so you must put so this one is wrong, so you must put feet and feet, okay, uh, at the numerator and of course the denominator part. And the last part, okay, so when feet is, of course the final answer where you get this is 316 times 1 meter over 3.281. Okay, so that will give you 96.3 meters. So another example here is converting 26.4 meters to feet. Remember, meter to feet. So the final answer should be feet. So therefore we need to cancel out meters. And if you want to cancel out meter, remember the conversion is 1 meter is equivalent to 3.28 feet. Therefore, how to put the meter or feet? Okay, it is either numerator or denominator. So 26.4 is in meter, and therefore if you wish to cancel out meter to turn the final answers into feet, then you put it, okay, top and bottom. Okay, the value you want to convert is you put it at the top, and of course the conversions you put it at the bottom part, which is at the numerator part. So therefore you can cancel out m, and last part is you can get 26.4 times with 3.281 divided, this one is feet, divided with 1. So therefore you can get 86.6 feet. Okay, so let's look to the examples here. If a car is traveling at a speed of 28 meter per second, is the driver exceeding the speed limit of 55 miles per hour? Okay, the question asks you to either the driver already exceed or not the 55 miles per hour. So we should convert it 28 meter per second. Okay, we should convert first to the miles per hour because we want to compare what is the value of the 28 meter per second when they convert to miles per hour to the 55 miles per hour. Okay, so how to convert it? Right. Okay, so let's look at 28 miles per hour, meter per second, 28. Okay, how to convert two units together? Okay, just now we did feet to meter, meter to feet, so that is only involve one parameters only. So in here we have meter per seconds, and if you want to convert from meter per seconds to miles per hour, okay, you must do it properly. Why? Because we don't want to get confused, because meter should be converted to miles and not the hour, and of course seconds we should convert it to hours. So we must do it properly for us to understand the concepts of cancelling, how to cancel a top to bottom or numerator and denominator. And of course, if you want to convert 28 meter per second, so start with 28, okay, meter and over seconds, okay, over seconds, so times with, okay, put a bracket over here and do the conversions. And of course, if you want to cancel m and replace it with the miles, and we should put miles at the numerator, because we have to put the meters at the denominator. So therefore we know that from the previous or from the earliest calculations, 1 miles is equivalent to 1609 meters. Okay, 1609 meters, and of course equivalent to 1 miles. Okay, and that's will give you, will cancel out m and m. Okay, but how about s? So s, we do it another bracket, you put another bracket over here. Okay, and if you wish to cancel out s is at the denominator level. Okay, it's at the bottom. So if you want to cancel s, so you should put 3600 seconds. Okay, that is equivalent to 1 hour, like this. Why? Because s is at the denominator and 3600 is at the numerator level. So we can easily cancel out s and s. Remember, if you wish to cancel out the terms, you must do it in a way that it should cancel out up at top and bottom. You cannot cancel out left and right. So therefore the final answer is given by 28 times with 1 miles times with 3600 divide with 1609 times with 1 hour. So you should write down as like this. So to get the value of 1.74 times 10 to the power of -2, pardon me, 62.6 miles per hour. So does it exceed the speed limit of 55? The answer is yes, because the speed limit is only 55 miles per hour, while the driver's speed is 62.6 miles per hour. Okay. A Porsche sports car can accelerate at 14 meter per second square. Determine its acceleration in kilometer per hour square. So this is something new, because it now involves s square. So how to do it? Okay, so let's look at how can we solve it. We have 14, okay, meter per second square, and obviously, okay, you want to convert it to kilometer per hour square. And of course, you can see here the square as the second part is also the square at the hour part. So that it will be the indicator of the good conversions, because when we have the question as when we have questions second square, so meaning that the time should also be square. And if the length is square, and of course the kilometer is also square. Okay, so that is the very good hint in terms of how you can deal with some things, with something related to the power of either quadratic or cubic. So let's look how can we solve this one. So 14 meter, again you put the second square at the bottom. Okay, 14 meter per second square. Now you times with in the bracket. So we should cancel out first the meter and the kilometers, because we want to convert it to meters. Remember, meter you convert it to kilometers. So 1000 meters, okay, is equivalent to 1 kilometers. Okay, so therefore you can see this is at the numerator level, and this 1000 meter is at the denominator. So we can cancel out later on. Right now, let's look at how the very important part, how to change the s square into the hour square. Remember, first you create a bracket over here, okay, and easily just put square at the outside of the bracket. Put the square outside of the bracket. Okay, and of course in the bracket just do a normal 1 hour to a second. So meaning that 3600 second over 1 hour. Okay, but remember one thing over here, make sure that you follow this kind of indexes. Remember, AB square is equivalent to A square B square. And you do have two things inside the bracket. You should multiply, you should square all the values inside the bracket. So remember this thing, okay? Right? And of course, how to cancel m? Yes, easily just cancel the m. And how about s square? S square is cancelled out. Remember this thing, okay? S square is already cancelled, but in the bracket there's still 3600 square. This thing is only the students always forget to square the 3600. Normally they will forget about this. Okay, so that is a good hint. 14 times with 1 kilometers times with 3600 square. Don't forget to square or else you get wrong answers. Times with 1000 times with 1 hour square. Okay, 1 is also square because 1 square is equivalent to 1. So you don't have to make you don't have to worry when you deal with 1, because 1, if the 1 is square, then it only becomes 1. So therefore the value should be equivalent to a certain value. So let's calculate. 14 times 3600 square, okay, divide with 1000, and the answer will be 1.8144, 1.8144 times 10 power of 5 kilometer per hour square, HR. Okay. So now you can continue with these examples on your own. So that will be the end of the chapter 1. So to be continued on chapter 3. So stay focused and stay tuned, guys. So I'll see you afterwards. Thank you.